In this video, we want to discuss the parts about sensors that are thermal and optical sensors. I'm not going to talk in great detail about thermal and optical sensors because actually a person could give an entire class on thermal and optical measurements, but we will give a little bit of an overview of the different kinds of thermal and optical measurements that are common. So first, thinking about temperature measures, the most common kind of temperature measure is the thermocouple. And the thermocouple is designed to take advantage of the Peltier effect. The Peltier effect is that dissimilar metals have a voltage at the junction. And then they're also designed to take advantage of the Thomson effect, which says that this junction voltage varies with temperature. Now, usually this relationship is defined by a power curve. So this is the voltage, and here it is as the function of temperature with constants A and B and so on. And there are some important laws that govern the operation of thermocouples. The first law, the law of homogeneous circuits, says that in a circuit that's composed of a single homogeneous metal, you cannot maintain an electric current by the application of heat alone. The second law, the law of intermediate metals, states that the net electromagnetic force or voltage in a circuit consisting of an interconnection of a number of unlike metals maintained at the same temperature is zero. So in other words, if you sum around the closed path, the sum of the voltages will be zero. And the third law, which is successive or intermediate temperatures, is illustrated in figure 2.13d, which we'll see on the next slide. This is basically you get an EMF E1 that's generated when two dissimilar metals have junctions at temperature T1 and T2, and E2 is for temperatures T2 and T3. So then it follows that you get an electromagnetic a voltage that results at junction C and D when the junctions are at temperature T1 and T3. And once again, the sum of those voltages around the closed path will have to equal zero. So you can see right here, which is what we were just illustrating. So we have two dissimilar metals at T1 and T2. They have a voltage E1. We have dissimilar metals at T2 and T3. They have a voltage E2. And so now if we look from T1 to T3, we see that the voltage is E1 plus E2. So this is the law that we just discussed. And these are just figures that illustrate some of the different laws that we just discussed with pictures. So the thermoelectric sensitivity, alpha, is known as the thermoelectric power, or sometimes called the Seebeck coefficient. And you get that when you take the derivative of voltage with respect to temperature. And so alpha is A plus BT, and so on. So alpha itself can be a function of temperature. So clearly this is a nonlinear effect. I do want to make one comment. This symbol E is showing up fairly frequently. That's just a voltage. The use of the symbol E or the term electromotive force is sometimes common when mechanical engineers talk about voltages. And so you'll sometimes see those referred to as E or EMF. Sometimes also you see that in the power engineering community. So don't be dismayed. I know in electrical engineering, when we see E, we tend to think that's referring to an electric field. In fact, in this textbook, that is typically referring to a voltage. So thermocouples have a couple of advantages. They have a very fast response time. Now fast is relative. Time constants of 1 millisecond. But in terms of the human body, that's fairly fast. They have a small size, down to 12 millimeters or a centimeter in diameter. Also relative, but still not bad. They're very easy to fabricate, and they have long-term stability. Their disadvantages are they give a relatively small output voltage, they have a relatively low sensitivity, and they need a reference temperature. This is just a circuit that illustrates, here is our thermocouple, and here's a circuit of how you would take the voltage output from the thermocouple and amplify it in an inverting amplifier to get an output voltage that's meaningful. So we will, in chapter 3, cover more about amplifier and inverting amplifier circuits. This is just to give you an illustration of the kind of circuit that's usually used for the thermocouple. The other kind of temperature measure is the thermistor. A thermistor is a semiconductor made of ceramic materials, and these are basically thermal resistors, and they have a very high negative temperature coefficient. So they react to temperature changes in a way that's opposite of how metals will react to such changes. In other words, the resistance of thermistors will decrease as temperature increases, and they will increase as temperature decreases. So here are some common curves of thermistor materials. Here is the resistance ratio of the resistance over resistance at 25 degrees C. So here would be our sort of reference point, 25 degrees C, where our normalized resistance would be 1. And then you can see as the temperature decreases, the resistance increases, and as the temperature increases, the resistance decreases. Figure B illustrates voltage versus current characteristics for a thermistor in air and in water, and you can see there are some differences there. The diagonal lines here would give the linear resistance values and show the degree of linearity at low current. So when we come down here to the low current milliamp range, you can see we follow a fairly linear path. The intersection of the curves with the diagonal line with negative slope will give you the device power dissipation. So thermistors are just a different way of making a temperature measure. They're typically operated at very low power so that you have a negligible self-heating. If you operate them at high power, then just the I squared R heating coming from the current will basically self-heat the device, so it interferes with its own measurement. The empirical relationship between resistance and temperature in a thermistor is given by this equation. There's a material constant beta, and that does vary slightly with temperature, but overall it can be treated as a constant as long as the temperature range is fairly narrow. And then T naught is the standard reference temperature in Kelvin. So here's the relationship between resistance. R0 would be the resistance at the reference temperature. The temperature coefficient is given by taking the derivative of R1 with respect to temperature and then normalizing that to RT. And if you do that, it comes out to minus beta over T squared. Thermistors are linear until self-heating becomes a problem. So basically can treat them as linear until the current becomes such that you get I squared R heating, and then they become nonlinear. Optical measurements. So there are a couple of significant things to remember about optical measurements. In optical measurements, you'll typically have a source, you'll have some transmission media, and you'll have a sensor. And all of these have curves that are dependent on how the material is responding to the wavelength of the optical signal. So if you send an infrared signal through the atmosphere and you produce that infrared signal with a light emitting diode, and then you're trying to detect it with a photodetector, the diode itself has a characteristic curve, the air has a characteristic curve that it will transmit, and the photodetector has a characteristic curve that it will receive. The second thing to remember is that a lot of times the transmission media is a fiber optic cable, which has its own characteristics. So those are two things to sort of keep in mind. Here is an example of what happens when you try to do a transmission through a media and then receive it with a detector. So if you look at figure A, this is an example of a tungsten light source. And a couple of different temperatures here compared to a light emitting diode. So you can see this tungsten light source. It has a really broad kind of range of emission. The light emitting diodes are fairly narrow. So over the wavelength here, you get a fairly narrow emission. And as indicated here, gallium arsenide emits in the infrared, gallium phosphide in the red, and gallium arsenide phosphide in the green. So you do tend to get these kinds of emissions. And then if you go with something like an argon or a helium neon or a ruby laser, you basically get line emissions, so single frequency emission from the laser as compared to the light emitting diode. what then typically happens is the light is filtered. And so if you have some kind of a filter that passes a particular band, and here's some examples of filters, and sometimes the filters are intentional and sometimes they're unintentional. If you have, a packaging or some kind of protective glass that covers the light emitting diode, then that's going to act as a filter. Here's some, just figure that indicates for glass, for germanium, for different materials, what they actually will pass and how they'll pass it. So you can see here crown glass has like a really flat area. If you don't want your filter to impact your output light, then that would be a good one to use. Germanium lenses are used to pass the longer wavelengths that glasses normally don't pass. Hemoglobin and oxyhemoglobin, these curves here, those are mentioned because that obviously is blood. And so the interesting thing is, is there a spectral range that can pass through blood? And yes, there is. Okay, then finally you have your detector. And notice we're not really talking, the transmission media here is glass and blood. We haven't really mentioned air because it's fairly flat. It's got fairly flat transmission over most light frequencies of interest. The human eye here, you can see, can detect the following wavelengths. So we're pretty much restricted to the visible range. And even within the visible range, it's not completely flat. So we tend to see better at the longer wavelengths than at the shorter ones. But then the detectors themselves will have a response. So here's silicon. And silicon clearly peaks here in this region. So it'll have the strongest response to light of this wavelength. And of course, if you're outside of that wavelength, then you won't have any response at all. So you can see what has to happen is your wavelength of your light source and your transmission media and your detector all have to have some area in common. And so what you see here on this bottom curve is basically the product of these three curves. So you can see that in silicon, for example, with a tungsten light at 3000 K, that you get this kind of possible combination of light that actually makes it to the detector, is detected, and gives you an output voltage or current. So different semiconductor materials will radiate at different wavelengths based on their band gap. We can't really do semiconductor physics in this class, but basically the difference between a semiconductor and a metal is that while electrons are free to flow in a metal, electrons in a semiconductor are not free to flow. They have to acquire a certain energy to jump the band gap in order to conduct and move. And so that energy is usually generated thermally, but it can also be generated optically. So this is just an indication of, and then of course when they, when the electrons or holes cross back to the base, the band gap, they emit at a certain optical wavelength. And so that's what this is illustrating. That silicon and gallium arsenide and gallium phosphide. These are the current voltage curves. Each one of them radiates at a different wavelength, and the band gap has a different energy. And the energy and the band gap are directly related. Now, once you have your emitted light, you then have to deliver it wherever you're going. One of the best ways to do that is via fiber optic cable. The reason a fiber optic cable is a good idea, in a fiber optic cable you have the fiber and then you have some kind of clad or coating that is on the outside of the fiber. And the optical engineer will design the index of refraction of the coating or cladding and the index of refraction of the fiber to be such that when light enters the fiber optic cable, for a lot of angles, you get total internal reflection. So you've met a critical angle. As long as you are below that critical angle, the light basically reflects and stays confined within the fiber. And there's even some forgiveness here. the fiber can be, within a limited extent, bent or curved, um, and still maintain this property as long as this angle doesn't get too large. So total internal reflection is a good thing because it keeps the signal confined to within the fiber and can deliver in a harsh environment the light to where the measurement's being made. So then you have to somehow receive the light, and photo detection typically occurs when you illuminate a diode. So a diode would be a p-type and n-type material placed in contact with one another. The current voltage characteristic for the diodes are shown here, and when you have irradiated junctions, it basically generates a current. So you can see that these are different levels of radiation. So this is 0 radiation. There still is the diode characteristic, but when you radiate with a milliwatt per square centimeter, you can see the reverse voltage is decreased and the forward voltage at a given location is also decreased. Current. So anyway, you can see how the how those things move when you irradiate them. So this is 10 milliwatts per square centimeter. You can see the reverse down here is pretty significant. So typically they tend to be operated in reverse bias mode because that tends to be a bit more linear. So you get a little bit more linear change with respect to change in optical radiation. So that concludes really at this point what I want to say about optical emission, transmission, and detectors. We'll talk a little bit more about it when we get to the section where we actually talk about biomedical instrumentation that involves photo emission and photo detection. There are a number of courses offered at Texas Tech from the nanophotonics people in solid state devices and nanophotonics and related areas. If you're interested in this, there's certainly a lot of courses that you can take on it. So we're not really going to go into it in depth in here other than what we've covered up to this point.